If I move that back, yes, they would get, yeah, they should be farther apart. There we go. All right, so we got the central bright spot right here. And then
You have dark spots.
dark band there, there, there. Oops, just a second. I moved that, so all those are invalid. Try that again. I'm seeing actually more than one pattern here. That's what's disturbing me. Probably enough. We'll try to identify, all right, the central bright spot, all right, identified right here.
So you got,
I am thinking that is not what I originally planned it to be. Go back to my Cornell plate. There we go. All right. That is not single slit diffraction. One of the reasons why this is coming out so much sharper than it did yesterday is the fact that that's a diffraction reading right there that I'm putting it through.
That is not single slit display?
That is not single slit. And if I use my imagination, I can see lines there. So this time, there's a clearly double slit there, yeah. All right. Once more into the breach. Kill the lights again and take a look. So very clear central bright spot right there. And it looks like there's a dark band there, dark band there.
Oh, well, I can't see this.
I think that's a dark band there. Some of these are blurring together, making it a lot more difficult.
is it supposed to be equal dark bands on either sides?
Should be. That's the central bright spot right there. Hopefully that's enough. And because I have so many lines on here, I'll just mark through the ones I don't want. So the first dark spot appears so basically about 0.65.
6'5" centimeters.
Yes. And we turn the laser off before I accidentally shoot myself in the eye.
0.06 meters.
You'll be fine.
Alright, so, D over two is, so assuming double slit, or assuming small angle approximation is valid, there we go, eventually words came to me. We'd have two n lambda over two, no, two n lambda over D is equal to y over L. Let's find out how close we are, and if we're off by roughly a factor of 2. Y would be 0.0065. L, 1.76, close enough. N was 1. You're sending the wavelength over D. Oh, I guess we need to know that information. Shoot it through the second one. That is a width of 0.195 millimeters. So D is 0.000195 meters. What do we get for the wavelength?
That's a 1.
So where are you looking?
0, 0, 0.
195.
Okay, 1, 1.
.6 times 10 to the -8. Might be off by a number there or something.
So it sounds like we're off by a factor of 20.
20,000.
2.
Yeah,
That same thing?
yeah.
Alright. What number did you get again? You had 3 point something?
3.6 to the -8.
Alright, the 2, we can deal with like that, that's easy enough. But then we're off by a factor of 10, so did I mismeasure something? So that distance right there, according to this, was 0.195 millimeters. So convert to meters, move it over a factor of 3, so I'm good with that. Because I shot it through, make sure I shot it through the right one.
I got 3.600 to the 7, -7.
Ah, I'm liking that a lot better.
I see my mistake. The .0065, I did 3 zeros.
Ah.
Not 2. Yeah.
Yeah, how many times have I told you, don't throw in the extra 0?
So the N was 0.65 centimeters?
3.60 times 10 to the -7.
3.60 times 10 to the -7. I had an extra 2 in there that I shouldn't have had, so that puts us at 720 nanometers, which is above the range, but
What was the N?
N is 1.
1.
It was I did the distance to the first dark spot.
Where did you get the 720 from?
I got low.
Oh, alright, so
I did not get that.
the 3.6 had an extra 2 in there that I mistakenly put down.
Okay.
So if I remove that 2, then,
Well, the 2 was a mistake?
well, actually, let's make sure I put the 2 in the right direction there. So we have,
Because if it was a mistake, then you'd be right, because, I did put the 2 there and I got half the wavelength,
Yeah, so,
which would make it, well, almost ultraviolet, so.
because you're solving for wavelength, which means that ultimately you would be dividing by that two.
And the 2 would go in the denominator.
Right.
Yeah, so if you don't divide by that two, you'd end up with 7.2,
Yeah.
which is where I got the 720 from.
I got 3.6.
Okay.
Yeah, so I got half that.
So it's the same formula as we did for the double slit, it's just the interpretation is different.
So there is no 2 there.
There is no two there.
There's no check.
And I think that it was, the Y was small enough compared to my length, that small angle approximation is decent enough. And I will say, just as a side note, that the double slit formula holds together longer than the single slit formula, that if you start getting into the, like senior level optics, that the equation gets far more complicated more quickly. But we will not have to worry about that. All right. That's all I would really want to, there's some additional stuff in chapter 37, but I'm gonna skip over it. Oh, wait, no, I do want to do polarization. Let me grab the polarizing filters. We talked briefly about what light was. Questions before I talk about polarization?
Polarization.
Yes, polarization.
Sunglasses.
Same type, same thing. Except we're using official round polarizing lenses instead of sunglasses. Way to dress appropriately for class.
I don't even know if they're polarized or not.
Oh, we can test that easily enough.
I think mine are, but mine are, they're not.
Well, we'll get the overhead set up and then we'll see, if we can, what's polarized. All right, so when we talked about the creation of light, it's an electromagnetic wave. And you basically have an electric field that's traveling in some direction, and then a magnetic field which is perpendicular to it. That's in my attempt to draw two different waves. One's going this way, the other one's going that way. Now, in reality, this is the way it's generally presented in textbooks. In reality, that electric field line, it's got 360 degrees of electric field, but the magnetic field is always perpendicular to it, however it's oriented.
So that's 3-dimensional.
Yes, that's my attempt at a three-dimensional drawing.
Draw a line through it, going the way it is. Yeah, that's better.
I should have drawn that line first.
Yeah, that's better.
And with red blue 3D film glasses, they probably would still look as bad. All right, so this is a specific orientation of the electric field, the magnetic field. They are always at 90 degrees from each other for an electromagnetic wave or from light of whatever the frequency is. But electric field is actually got 360 degrees of orientation. So right now you're being bombarded, your eye is getting hit with the electric field basically every direction. What the polarizing filter does is it blocks orientation of the electric field. So if I have, coming at you, I have electric field lines that are basically going in all directions, and the magnetic field perpendicular to each individual one. If I set up my filter so that set up the filter so that basically the atoms align in a particular orientation, it's gonna block out everything that's going against it. So the only stuff that will make it through is the vertical piece of it. So if I have one coming in like this, and I'm blocking it, then I'm only allowing the vertical to come through, basically, it's just the vertical component that is gonna come through. And so what you'll end up with is less than what you started with. If that's basically the magnitude of my electric field, but that's the vertical size of it, and then same down here, what's gonna make it through is something that is less than what you started with. So originally that long, but the polarizing filter cut it down to here. The more horizontal it is, if it's completely horizontal, there is no vertical piece to it, it all gets blocked.
So how does that like allow you to see in the water better? I know it's like a big thing with fishing, you put on polarized glasses, you can see into the water more clear.
I assume it cuts out the glare.
I guess.
So sunglasses, the polarized filters of sunglasses mainly are cutting out reflection. That when it bounces up, I'm trying to remember, I think the electric field that survives the reflection mostly is horizontal. And so you have a filter going this way to block the reflection. I could be back 90 degrees off on that, but that's the way it was
I think
explained.
you're right, because, my glasses, if I turn my head like this, the reflections come through.
Oh, okay,
Okay.
there we go.
Yeah.
Now, pull up the overhead projector and start playing around with some polarized filters here.
Be careful.
I haven't seen one of those in a long time.
There are possibly just one of us left who use it. Oh, no, the Sassen uses it for one thing. The Sassen?
Oh,
Here.
Yeah. Because it,
All right. It's not as bright. Ooh. There. All right, so that's blocking out half the light, and the orientation of that filter is some way. I don't know specifically what it is. It might be marked on here. There are 2 marks on it, and I don't know if that's telling me the orientation of what's allowed or what's being blocked. Let's see. Oh, that one. There we go. So right now, there's 2 marks right here, so that's sort of an orientation of it. Now, I'm gonna take another filter, and if I put it right over it with the lines in the exact same place, it should be roughly about as bright as it was before. It's a little bit darker. That's probably the best we're gonna get right there. But if I take that top filter and I rotate it 90 degrees and put it on,
it'll block everything.
because any of the light if I only allow vertical light in past the first one, and then I put the other one perpendicular to that, it's gonna block out, well, everything that was vertical before.
so you've made welding goggles.
What's that?
You've made welding goggles now.
Oh, okay. Now, if I then take this, let's try to keep that orientation there. There we go. And now I'm going to stick something in between it. And still everything's blocked because the one I put on, the middle one is the same orientation as the top one. But I'm going to take that middle one and I'm going to rotate it 45 degrees. And you can start to see some light come through. And all I'm doing is rotating the middle one, and apparently rotating the one underneath it. All right, so that blocks it all out. The middle one. Third hand would have helped. There we go. And you can see some of the lights coming through by putting the middle one there. I remove the middle one, it's dark again. Put the middle one there, and suddenly you can see through. So what's happening by putting the middle one in there, I have light coming in from all directions. I orient it so that only the vertical stuff comes up or goes through. When I had just the two on there and I put it perpendicular to it, it blocks out everything that doesn't have a component horizontal. When I put the middle one in there, allowing only things at that angle, well, every single one of this light has some component at that level. And so what then gets allowed through is stuff like that. And the bottom one, oriented like this, well, each of these has some component in that direction. And it should be getting darker and darker as we go because we're cutting out light every time. But some light is making it through because we get part of the light that was coming in before.
So you put a fourth one on there.
You can get smaller. Less one.
Yeah, at some point, these eyes won't be able to tell. So I take that one, and I put that one at a 45-degree angle. And this one, all right, so some light is getting through there. Well, all of that here for nothing. I lost track of what the first one was. All right, so you got the three there,